Okay, yeah. Welcome back. So we've just released the first assignment. So if you go to the course website, you can see these lectures, quizzes, and exercises, and here's the assignment. So it's to get you started with TensorFlow. So have a look at this. So we've got links here. So we're not going to cover too much about TensorFlow in the lectures. I gave you a little bit of a demonstration last week, but we've got links here to help you along the way. We recommend, as I mentioned, we're trying to get you to use as much as possible the core, kind of more low-level aspects of TensorFlow rather than the more high-level ones. So that's why we've recommended that you start off with this tutorial with the low-level introduction. So there's a link to this here. So it goes through and explains in more detail about graphs and sessions and so on. And if you have any difficulties with this, please go along to the lab sessions and ask questions or post questions on the forums. So basically what you'll have to do here is write some TensorFlow code to define a few models. So it's split up into part 1 and part 2. So part 1 is just defining a ReLU and perceptron, and part 2 is defining 3 different models. So there'll be a single layer network, a 2-layer network, and a convolutional network. So we'll be talking next week about the structure of convolutional networks. And when you submit, so the tests for the test for part 1 will be run when you actually submit. So when you submit your code, it'll run some tests to make sure that it's in the right format and you know, that you're not making any syntax errors and so on. And then the test for part 2 will be run afterwards, after the submissions are closed. And just a quick note about version. So we're encouraging you to install TensorFlow 1.9, which is the latest stable version. I think they may have released 1.10, but we're sticking with 1.9. But when the tests that are run at submit time are actually, unfortunately, using TensorFlow 1.3 because the lab machines are configured in 32-bit mode. But it shouldn't make a difference because we're using the parts of TensorFlow that are basically common between 1.3 and 1.9. So if you do spot, there shouldn't be any issue about version numbers, but if you do sort of come across any issue that we may not have come across, please post a message or email us or ask in the lab session and we'll look into it. Okay. So have a look at that and let us know how you go with it. Good. Okay, so what we're going to do today is to continue our discussion of variations on backprop and then also talk about how to analyze the geometry of hidden unit activations. Oops, we don't want to see them all. Okay, so some of this we started with last week. We were talking a little bit about basic probability. We talked about dice rolls. If you throw a 6-sided die, you get 6 atomic events which are equally likely, and then you can put them together into compound events such as the probability of the number being even or the number being less than 3. We looked at Venn diagrams and inclusion-exclusion. We talked about continuous probability distributions where we're actually, to turn it into an actual probability, you have to look at the area of a small rectangle. And we were discussing this Gaussian distribution, which is going to be fundamental to a lot of what we do, especially when we get to variational methods. So try to memorize this formula and keep it in mind. By the way, I brought a copy of the textbook along today. This is what it looks like. Right, so we're going to discuss cross entropy, weight decay, and momentum. So this is the formula for cross entropy. So this involves replacing taking the squared error cost function and replacing it with this cost function. So the way I was explaining it last week was that this is particularly useful in cases where there's a disparity between the number of positive and negative examples. So because this error function blows up to infinity, if the target value is 1, but let's say the target value is 1, as the output of the network approaches 0, the cost function actually blows up to infinity, and the same thing happens if the target is 0 and the output is 1. So it's very heavily punished for giving a definitive answer that's wrong. So if this prevents the network outputs from saturating to wrong values and forces them to stay in the middle somewhere and make some kind of discrimination between the classes, So that's the kind of moralistic argument. But there is a more kind of mathematical argument for this formula, which we're now going to discuss. Now, in order to do this, we have to look at this idea of maximum likelihood. Okay, So here's where we have to get used to the terminology of statistics and information theory and probability and machine learning. So we talk about a class of hypotheses. So the hypotheses, if we're talking about a neural network, the hypothesis is normally we have a fixed architecture in mind, and the hypothesis is the set of weights for that network. It's called a hypothesis. If we're trying to fit a straight line, then it would be the slope and the parameters of that linear function. And then we observe some data, and so we try to calculate the probability of the data being observed conditioned on that hypothesis. So if that hypothesis is really a true representation of the underlying process, what would be the probability of the data being observed? So that's called the log of a probability is sometimes referred to as a likelihood. So the idea of maximum likelihood is we want to find D is fixed. D is just the data that we observe. We can't do anything about D. But what we want to do is from a certain class of hypotheses, we want to pick the hypothesis that maximizes that log likelihood. We want to pick the one that maximizes the likelihood, but if we maximize the log of the probability, that's the same as maximizing the probability. And if it's the log of a probability, we refer to it as a likelihood. Right, so this is called the maximum likelihood principle. Choose that H which maximizes the probability of D given H, or maximizes log of the probability of D given H. So if we look at this line fitting, we've all sort of, I think you've all been through this process in high school or in first year mathematics, where you're given some data and then you try to fit a line to those data, and the way we traditionally do it is you find the line which minimizes the sum of the squares of the distances from that line to the data. So I think you're all familiar with this process, but you may not have until now, you may not have thought about where this comes from or why we do it in that particular way. So that's what I'm going to talk about now. So, first of all, the thing you've got to really ask yourself is, why is it that the data don't lie exactly on the line? I mean, in a perfect world, all these points would lie exactly on the line, and that would be that, right? So why is it that they're a little bit off the line? Well, there are two reasons for this. The first is what we discussed. There could be outliers, there could be mislabeled data. So it is, when you see something that's very far away like this, it's possible that someone made a mistake and typed in a number wrong, and maybe this should have been something else. So there's sort of in some cases you can get gross error of that kind, in which case you may have to just throw away that sample or go back and clean it up and try to see try to figure out what the correct measurement was. So that's one issue. But let's assume that hasn't happened. Let's assume that all the data is correctly labeled. Why would it be? If you look at these ones that are actually close to the line but not quite there, why is it that they're not on the line? Well, often this is because of noise in the apparatus. So if it's a physics experiment, if you're dangling a pendulum on a string, and you're measuring the time it takes to swing back and forth, it's affected by air particles or gusts of wind, can make a bit of a difference. if you're doing an experiment that relies on some sort of electronic measurement device, then there could be some static noise, there could be some electromagnetic field, some interference from a mobile phone, or there's all these kind of small factors. We don't really know what they are, but we assume that this kind of noise arises from a combination of a lot of small things that get added together. And this is where this law of this central limit theorem or law of large numbers comes in, that if you have a large number of small random variables and you add them together, the sum of all those random variables will follow this kind of normal distribution. That's what the central limit theorem tells us. That's why so many things in life are distributed on this kind of bell-shaped curve. So there's kind of a probability around each point here. There's a kind of probability of data being observed. So it's highly likely that the point will be observed here. It's a bit less likely that the point will be observed, that the data will land here, and it's somewhat more unlikely. So this graph here is meant to show the probability of the data happening that far away from the line. So this is somewhat smaller than that, but not outrageously small. This one is perhaps outrageously small, but maybe that one's an outlier. Okay. So if we go back and look at our equations here, this is what's actually plotted. So let's remind ourselves what these numbers actually are. So DI is the height of the data. XI is the coordinate on the horizontal axis. H of xi is the corresponding point on the line, and di is the actual data point. So di minus h of xi is the distance from the data point to what the line would have predicted. And the formula for these little Gaussians that I drew is like this. E to the minus di minus hi xi squared divided by 2 sigma squared with this normalizing constant. So there's some sigma. That Gaussian noise has some standard deviation. We don't actually know what sigma is, but as you'll see in a minute, in this particular situation, we actually don't need to know what sigma is. That's sort of the magic of this. Okay, so that's the probability of each data point, and to get the probability of observing all of those data points, we multiply those probabilities together. So if there's m data points, we take the probability from I equals 1 to m of that expression. Now, what happens when we take the log of this? Well, when we take the log, the log of a product is a sum. The log of a product is the sum of the logs of the individual terms. So the product turns into a sum. Now, the log of e to the power something is equal to the something, right? So we pull that out and we say, okay, minus 1 over 2 sigma squared di minus hxi squared. Now, what about this constant? Well, the log of that is minus log of sigma minus a half log of 2 pi. Okay. Now, remember, we don't have any control over sigma, so minus logs. We want to try to we want to find the h. H is the only thing we can control. We want to find the h which maximizes this expression. So this constant here is something we have no control over. So if we're maximizing this whole thing, then we can chop this off. We only need to maximize this. And then we don't have control over this 1 minus 1 over 2 sigma squared either. So what we effectively want to do is maximize the sum of minus di minus h of xi squared, but because there's still a minus sign here, so what we want to do is minimize the sum of di minus h of xi squared. So this is where that concept of the least squares fit actually comes from. It comes from that Gaussian. So if we can find the line which minimizes this sum, then that is the line that satisfies the maximum likelihood principle, in the sense that it maximizes the probability of those particular data being observed. And this is sort of the beauty of this, is that we didn't need to know what sigma was. It actually doesn't matter what sigma is. In any case, we need to minimize this sum squared error. Okay, are there any questions about this? Good, okay, so that's sum squared error. Now what about cross entropy error? Well, if we're doing a classification task, the output is either 0 or 1, so we have to come up with a sensible interpretation of this probability of D given H. So the data that we're observing, we assume is 0 and 1. Now, in fact, actually, this formula does work when the data is not 0 or 1. It's called in that case, it's called the Kullback-Leibler divergence. But we're not going to do that generality. We're just assuming that what was observed is either 0 or 1. So if we're trying to classify transaction as fraudulent, we assume it's either fraudulent or it isn't, or email either is spam or isn't. We assume there's a definitive class for each training item, which is either 0 or 1, but the network or the line, it doesn't matter whether it's notice this, sorry, just to go back to this, the fact that it was a line doesn't really matter here. H of xi, if this is a neural network, then what I'm saying is that H of xi is the output of the neural network, and we still would want to minimize this sum squared error. Okay, so let's say we have a neural network, and for a certain input xi, it's producing a number between 0 and 1, which is H of xi. How do we interpret this as a probability? Well, let's think about this. So if H of xi is 1, then we would interpret that as saying that the probability of it being 1 is 100%, right? If H of xi was 0, we would interpret that as the probability of 1 being 0. Now, what if H of xi is 1/2, that's in the middle? Well, we would interpret that as saying that there's a 50%, if we wanted to interpret it as a probability, if H of xi is 1/2, that means a 50% chance that the answer is 1 and a 50% chance that the answer is 0. Because the true answer in this case must be either 1 or 0. It can't be anything in between. Now, what if HI was 0. What if H of x, if the output of the network was 0.8, we would interpret that as saying that the probability that it's 1 is 0.8 and the probability of it being 0 is 0.2, right? If it's 0.8 means there's an 80% chance that it's true and a 20% chance that it's false. So there's a natural way to interpret these outputs between 0 and 1 as a probability. Okay, so the probability, if the output is H of xi, that means the probability of it being 1 is H of xi, and the probability of it being 0 is 1 minus H of xi. Is everyone with me here? Okay, so we can write this. We could think of this as just we can think of this expression here as just a mathematical trick to combine these two expressions. Because if di is 0, then this term disappears. If di is 0, this term disappears because this raised to the power 0 is 1. And this raised to the power 1 is itself, right? If di is 1, this term will disappear and that term will just become h of xi. So for our purposes in this course, it's reasonable to just say that this third line is a fancy way of combining the first two lines. Now, as I say, if you want to think about the case where di is between 0 and 1, then you can go and study yourself about the Kullback-Leibler divergence and so on, but we're not going to get into that. Okay, so we have this. Now, once we have that, then if we take log of this probability, that's equal to di times log of h of xi plus 1 minus di times log of 1 minus h of xi. And we want to maximize this, but so we want to, we're used to thinking of it as a cost to be minimized rather than something to be maximized. So we take the negative of this, and that's what actually gives us cross entropy. So remember, this is the formula I wrote down for cross entropy. It's exactly the same, except that it's minus. Okay, so there's actually a logical mathematical foundation to this formula. Okay, any questions about this? All right, so that's cross entropy. Now, the next variant I wanted to talk about is weight decay. Now, before we talk about this, we need to talk a little bit more about probability. Yes, you got a question?
Was that similar to the cost function for logistic regression?
Logistic regression. It is related to this, yeah, and it's, let me think about it. I think it's the same. Logistic regression, yeah, I think it's the same. Logistic regression, I think, works when there's multiple, you can have multiple classes. So this is the case where there's just two classes. But the logistic regression is the same as this, but you can have multiple classes. Yeah, good question. And this is kind of related to softmax as well, but a bit slightly different. Okay, so right. So before we get to weight decay, we have to talk a little bit about conditional probability, and this is going to be we need to understand this for other parts of the course as well. So I listed probability as one of the kind of assumed knowledge for the course, but because it's so important, I'm going to go through a little bit about it, and some of you, of course, may have seen this in a previous course, but it is useful to just revise it. So for those of you who haven't seen this example before, this is to do with going to the dentist. So there's three things involved here. One is whether you have a toothache or not. You know, you go to the dentist sometimes just to have a regular checkup, or sometimes you wake up and you have a toothache for a few days, and because of that you go and make an appointment and go to the dentist. And then this is what you're sort of concerned about, is whether you have a cavity in your tooth. It's like a hole in your tooth that needs to be filled. And then this, just to explain what this catch is, you know, when you go to the dentist, they often have this hook device that they kind of slide around in your teeth and behind your teeth. Now, what they're actually doing there is they slide that hook behind your teeth. It's hard for them to see the back of your teeth, so they sort of slide this hook along, and if there is a hole in the back of your tooth, then that hook may get caught in the hole. The hook may catch in the hole. So if it catches, that provides additional evidence that you have a cavity. It's not conclusive, but it's supporting evidence. If it doesn't catch, then it's less likely for you to have a cavity. So this is just an example taken from an AI textbook of the relationship between these three different probabilities. So there's 8 possibilities altogether. And this, you can use this joint distribution to figure out all the kind of individual probabilities. So if we want to know what's the probability of having a toothache, this is sort of assumed to be in a population of, we assume that this is in a town where people eat a lot of sugary foods, so it's very likely for people to have cavities and toothaches. So if you add up all these 4 numbers, if you add up all these 8 numbers, the sum is 1. If you add up these 4 numbers, it turns out to be equal to 0.2. So this is saying that in this particular place, on any given day, 20% of the people are wandering around with a toothache. Good question. I think the question was, is this everybody or is this just the people who come into the dentist? Yeah, very good question. I think it's the people who come into the dentist. Yeah, so they may come in because they have a toothache or they may just come in for a checkup. Yeah, so yeah, maybe it's not the general people walking around. Okay, very good question. I'm glad you asked that question because that kind of leads into the idea of priors. And then you can make logical, this is sort of like a Venn diagram except using rectangles instead of circles, right? So if I ask what's the probability that someone has a cavity or a toothache, you add up these 6 numbers and it's a little bit bigger, 0.28. But then we can talk about conditional probabilities. So if we have 2 random variables A and B, we can say, well, what's the probability of A given B? What's the probability of A conditioned on B? Or the probability of A given B. That means among the situations where B, if we assume that B is true, then what's the probability that A is true? So, sorry to jump around, but I'll just go back to that Venn diagram. The probability of A given B is, the way we think of it is, well, we know that B is true, so we're kind of restricted to this area here, and then we say, well, within that, what's the probability of A? So it would actually be this area here divided by that area there. So the probability of A given B is the probability of A and B divided by the probability of B, right? So we see it here as a Venn diagram. This again is exactly the same thing, but just with rectangles. So if I say, well, what's the probability? It's sort of been reversed a bit here, but if you've got a toothache, what's the probability of not having a cavity? Then there's like a Venn diagram. So the red box is the people who have a toothache, and then within that, the green box is the people who don't have a cavity. So the probability of not having a cavity given a toothache is the probability of not cavity and toothache, which is the green box, divided by the probability of toothache, which is the red box. Okay? And when you work this out, it turns out to be the top is 0.08 and the bottom is 0.2, and so the ratio is 0.4. So 40% of people who come in with a toothache don't have a cavity, which means that of the people who come in with a toothache, what fraction of them do have a cavity? 60%. Good. You're awake. Okay, so Bayes' rule. Now, we often think about this as cause and effect. So this is, what did we have here? Probability of cavity given toothache, right? So the toothache, in this case, the cavity is the possible cause of the toothache, right? So it doesn't have to be this way, but we usually use it to calculate the probability of the cause given the effect. So if we think that A is the cause and B is the effect, then that's usually the way we think of it. So the probability of the cause, we know, we kind of, the model tells us what's the probability of the effect given the cause, but then we want to know if we've observed the effect, what's the probability of that cause given the effect, and it's equal to the probability of effect given cause, times probability of cause divided by the probability of effect. Here's a couple of examples. Again, some of you may have seen this before, but I've tried to make it slightly more complete here by splitting up the sensitivity and the specificity, right? So this is just medical diagnosis. So you say, you've got a test for a certain type of cancer, and only 1% of people have that cancer, and then you have a test, and the test has a sensitivity of 98% and a specificity of 97%. So I've split this up. Sometimes people just talk about the accuracy of the test, but it is often useful to split it up as false positives and false negatives. So what this means is, what these words sensitivity and specificity mean is that if the person has cancer, then the probability of a positive test is 0.98. But if the person doesn't have cancer, then the probability of a negative test is 0.97. Right? So then the question is, if someone does test positive, what's the likelihood that they have cancer? So we can draw this as a kind of diagram of cause and effect. For a random person, before we did the test, so this is called the prior. If you just pick a random person and you haven't yet done the test, the probability that they have cancer is 0.01, right? That's our prior. It's called prior. We call it a prior because it's before the test. After we've done the test, well, if they had cancer, then the probability of the test being positive is 0.98. If they didn't have cancer, it's only 0.03. So this is kind of like a Venn diagram, but we have to extract the information from these four outcomes, right? So if we ask if the test is positive, what's the probability of the person having cancer? So there's two situations where the test can be positive. That's here and here. So the probability of them having cancer and the test being positive is the 0.01 times 0.98. 0.01 times 0.98 is 0.01. And the probability of them not having cancer and the test being positive is 0.99 times 0.03, which is 0.03. So the probability of them having cancer is this divided by this plus this, right? So it's 1/4, right? So this is often used to test the people's ordinary. A lot of people who haven't been trained in statistics are very kind of have very unrealistic ideas about this. They sort of think, well, because the test is 98% accurate, they think it's very likely the person would have cancer. But when we take into account the fact that the person was very unlikely to have cancer in the beginning, it's the likelihood is really only 1 in 4. Okay. I just tried to come up with a slightly different example here because the other example is a little bit sort of hacked. Let's say you've got a company and you've got 2 different factories that are manufacturing light bulbs for you, and some of them are defective, and if you have a defective light bulb, what's the likelihood that it came from one factory or another? So this is exactly the same sort of idea, but just a slightly different context and more even probabilities. So let's say 40% of your light bulbs come from factory B and 60% from factory A. Factory A, 1% of the light bulbs from factory A are defective, but 2% of the light bulbs from factory B are defective. And then you ask, what is, if you just pick a light bulb at random and it turns out to be defective, what's the likelihood that it came from factory A? So again, these priors, if it comes from factory A, the probability of it being defective is 0.01, and if it comes from factory B, probability is 0.02. So again, we have exactly the same kind of picture, and the probability turns out to be 3/7. So it didn't in the case of the medical diagnosis, we changed our probability a lot based on the test. Before we did the test, we thought there was only a 1% chance the person would have cancer. After we did the test, we thought there was a 25% chance. So that's a big difference. Here, we do change our opinion, but not quite as dramatically. So before we found out that the light bulb was defective, we would have said that there was a 60% chance it came from factory A. But after we know that it's defective, we change our estimate to, instead of 3/5, we change it to 3/7. Okay, so, but that's still a change. Yeah, because, so the fact that it's defective does give us new information. Factory B is more likely to produce defective bulbs than factory A, so we increase our estimate that it came from factory B and decrease the estimate that we came from factory A. So this Bayesian, there's a sort of philosophy that goes behind this Bayesian reasoning, is to say that there's always some prior. With the maximum likelihood, we didn't have any prior, but with Bayesian reasoning, there's always some prior, and then we get new information, and the thing after the new information is called the posterior, and sometimes we make a whole where are we? Sometimes we make a whole series of observations, and so we would start with the prior, and then we make one observation, and then we get a posterior, but then the posterior for the first measurement becomes the prior for the second measurement. And so it eventually can become a kind of dynamic process where the posterior for the previous measurement always becomes the prior for the next measurement. All right, so let's try to work this back into our terminology of machine learning. So remember, we're talking about hypotheses, and then we're talking about data. So we have the probability of data, a particular hypothesis producing certain data. So with maximum likelihood, we just maximize that, but then the Bayesians come in and say, well, really what you want to do is maximize the probability of the hypothesis given the data, and to do that, you have to take into account of the probability of the hypothesis as well. So some hypotheses may be a priori more likely than others before you even observe the data. Okay, so what has this got to do with neural networks? Well, with the most common assumption that we make is that we assume that certain weights are more likely than others. We assume that smaller weights are more likely to occur than larger weights. Right, so we put, again, here's this Gaussian distribution. We compose this on the weight. So we say that before we've seen any data at all, we assume that the likelihood of a particular set of weights is a product of a Gaussian distribution on every weight. So e to the minus lambda over 2 times the sum over j of wj squared. Now here there is a standard deviation in there somewhere, and we have to make it we have to make an assumption about what it is by choosing that lambda. Okay, so if that's the probability of the weights, okay, so if with maximum likelihood we were just maximizing this probability of d given h, but now we're going to maximize this whole expression. But remember, we don't have any control over the data, so we can't make any difference to this denominator, but we can make a difference to this because we're choosing h. So what we're actually maximizing is this multiplied by probability of h, and so the cost function, the sum squared error cost function, as we discussed before, means that we have to minimize this term here, the sum of the target output minus the actual output squared. But because we're multiplying by this term, we have to add the log of this term as well, which is actually this, right? So, and this is called weight decay. Now, why? So remember, I was saying there's always like a mathematical explanation and then a kind of hand-wavy explanation. So what I've shown you here, I've shown you the mathematical explanation first, and now I'm going to tell you the sort of hand-wavy explanation. Now, oh yes. Yep. Yeah. Yes. Well, remember we're minimizing this. Because there was a minus sign here, we want to maximize this, but there's a minus sign, so now we want to minimize this. We want to find the weights for which the sum of these two things is minimal. Who was asking the question? I'm not sure. Does that answer your question, or you still think there's a question? You still, can you?
Yeah, the fact that the term exists means that the weights are always have an impact regardless if they're large or small. If they're small, that will just mean that the second term drops off and the first term remains.
Yeah, if they're small, it's a trade-off between these two terms. Yeah, if they're small, then the second term drops off and the first term remains. That's right, but it might be quite high. If there's zero, if the weights are zero, the second term would drop off completely, and only the first term would remain. But the cost function, the error might be quite high. So what we want to do is we want to find weights which bring down the cost function but are not too large. This kind of fits in a way with Occam's razor. So we talked about Occam's razor. The simplicity of the model is like the number of weights. But here what we're saying is, well, it's not about the number of weights, it's the size of the weights. if the weights are smaller, we consider that to be a simpler model in some sense. Yeah, so if we can achieve the same error with smaller weights, then that's better. That's sort of the logic behind this, I guess. Yep?
If we are using the normalizing constant to reduce overfitting, would it be more possible? Would it be more likely that we normalize every single weight instead of normalizing all weights, the sum of all weights as a whole? Because surely it's some weights that's causing the overfitting rather than the entire weight.
Okay, so the question was some weights rather than all weights. So this is, okay, let me think. So are you asking whether you could have a different, so one of the problems with this is it gives us an extra parameter to play with, okay? We have to make a choice what lambda is, and normally we choose a lambda which is quite small so that that term doesn't, you know, a typical choice for lambda is about 0.00001. You know, 10 to the minus 5 would be a typical choice. So the idea is like you're putting more, if lambda is sufficiently small, you're kind of putting the more emphasis on this actual cost function and, you know, just a small kind of component on the weights. But you were saying, but normally we choose the same lambda for all weights. So maybe you were saying we could have a different lambda for different weights, or?
Yeah, I'm thinking about having different lambda values for different weights, because in this case we would reduce the overall weight rather than individual one. I mean, we reduce all of them instead of just some of them, because the overfitting is usually caused by some weights being too large.
Right. It's a good question, but you would have to choose which weights are more important than others. Yeah.
But isn't the new weight calculated based on the size of the weights? It's like the error function times the...
I think, okay, so I kind of see what you're saying. I mean, let me put it this way, the one area where one thing you might do is say, well, I've got bias weight. You know, you could treat the bias weights different from everything else. You could say, well, I'll have a different lambda for the bias weights compared to the other weights. That maybe is reasonable. But other than that, it's very hard to sort of say which weights you want to keep smaller. Yeah. Okay, just a couple more comments about this. I mean, one of the just to go back to this Gaussian distribution, one of the reasons you might ask yourself, well, why should I choose a Gaussian instead of, you know, why am I minimizing the sum of the squares of the weights rather than some other function? One of the beautiful things about this Gaussian distribution is that it's radially symmetric. If you have 20 weights and you multiply a Gaussian distribution in each weight, you actually get a distribution which is like spherical. Yeah, it doesn't. It's preserved if you kind of rotate the weights around and so on. So it's got this kind of nice mathematical property, and it's really, I guess, it's actually unique. It's really the only function that has that property of being spherically symmetric. Okay, so a couple more things about, let me just go back to backpropagation for a minute before to try to make the next point. If this, yeah, sorry, I just wanted to go back to this. So, one of the motivations for this weight decay was that if the weights get very large, then you tend to end up in this part of the activation function where it's like very, very flat. So you kind of lose the flexibility in the network. Now, in a practical terms, when you add the weight decay, it kind of forces the weights to stay more in this region, and then the gradient is bigger, and so you've got more kind of flexibility to learn. So it kind of prevents what we call weight saturation. Yeah, once the weights become really big, it becomes harder for you to keep learning. It's kind of like the way children can learn better than the older you get, maybe the harder it is to learn new things. So the same sort of thing can happen with the neural networks, and the weight decay kind of keeps them young in some sense by keeping the activations within this region. Now, it's also sometimes referred to as elastic weights. So the reason for the term elastic weights, those of you who are familiar with physics might recognize that this is also like the formula for the kinetic energy of a spring using Hooke's law. So we have this sort of image of these weights as like the weight is on a spring, and there's a force there's a force that's pulling the weight back towards zero, and the magnitude of that force is proportional to the size of the weight. So if the weight is twice as big, then the force pulling it back is twice as big. So it's this nice kind of physical analogy of these weights, the force pulling them back towards zero. Good. You guys asked very good questions. Does anyone else have any other questions about this? Yeah. So you'll see this later on when we look at specific example. If you read papers where people talk about training neural networks for Atari games or whatever, there usually will be something in there saying, yes, we used a weight decay of this value. Lambda equals such and such. Yep. If it's ReLU, it's less of an issue. Yeah, sometimes people don't use it at all. Yeah. Okay, so the final thing I wanted to talk about is momentum, and then we'll take a break. Now, okay, so I want to draw. Let me try to use the document camera to explain this. So the main situation that this deals with is if I can try to do this, people who are watching the video, let's imagine, sometimes you get a situation where we've talked about different landscapes, and sometimes you get a situation where the fitness landscape is kind of shaped like this, like a rain gutter, but on its side. So you have a sort of situation where it's curved up at the sides like this, but then it's sloped at a very slight angle. Yeah, this can happen. So in that situation, if you start here, if you sort of go back, if you oscillate back and forth like this, you're not really making any progress. To really get to a lower cost state, you have to sort of move in this direction. Yeah, but because the thing is shaped like this, the main component of the gradient will actually be like this. So you can kind of get this situation where you oscillate back and forth. You go here, and then here, and then here, and then here, and only make very slow progress in the direction that you want. So the way momentum works is you actually take a running average of these gradients. So you say, all right, well, you noticed if you took two successive, the gradient is a vector, and if you took two successive gradients and added them together, then it could perhaps, well, if you took several of them and added them together, then these oscillations, the oscillations in this direction might cancel out, and the combined vector might actually be in the direction that you want to go. So rather than just we could make 10 observations and then add those gradients. We could do it as a kind of batch learning, but in some situations what we do is we just treat it as a kind of running average. So this is how it works. So this is the gradient, right? So remember, if in normal gradient descent we would just say W equals W minus eta times this value here. But what we're doing now is, like, computationally we create a new array to store the weighted average of these the running average of these differentials. So we say, okay, I have this number dW which represents an average gradient over several recent examples, and then when I observe a new example, I have this number alpha. A typical value for alpha might be like 0.9. So I'm saying, okay, my new estimate is going to be 90% the same as my previous estimate, but I'm just mixing in 10% of the new gradient. So this kind of, more roughly speaking, this maintains an average of the gradient of the last 10 examples. It's not quite equal to that because it's a running average, but it's a running average of roughly the last 10 or 20 examples, but with the weighting decreasing, the more recent examples weighted more heavily. So we just, we adjust this, and then, so if this works out, in the ideal situation, those sideways oscillations would be dampened out, and when we do this, we can increase the learning rate. So the downhill motion would be amplified by a factor of 1 over 1 minus alpha. Okay, so this is called momentum. So, like, the main motivation, as I said, is this idea of the sort of the rain gutter. Well, okay, let me explain this in two ways. So, yeah, there's another situation. The thing may be just very flat. If you get into a region where the gradient is just, the landscape is very flat or only slightly tilted, then this will help you to navigate that region quicker. It also may help you to get out of small local minima. Thank you. So if you have a little bump along the way like this, then the momentum, if you're lucky, may just sort of, instead of getting stuck here, may help you to sort of just get bumped out of there. Another way to think of this is as an intermediate between batch learning and online learning. So we talked about the difference between batch learning and online learning. If you do batch learning, it effectively does this in a different way, because you're dividing the data into batches of 200, let's say, and then you're adding up the gradients for all those 200 examples, and then you're making a change. So batch learning kind of achieves the same sort of thing as this, but there are some situations where we get if it's supervised learning, we often don't have to bother with this because we're going to do batch learning instead. But when we get to reinforcement learning, there are some situations where we have to take the examples one at a time and it's not feasible to break them into batches. So this kind of gives us that benefit of batch learning without actually doing batch learning. Yeah. And then there's a couple of other things. We're not going to really talk about this, but I'll just mention it briefly. So there's more sophisticated methods than momentum, but which rely on second derivatives. So if you've got, say, 20 weights in your network, normally we just take the derivative of the cost with respect to each of those 20 weights. Now these methods, they take, for every pair of weights, they compute the second derivative with respect to those two weights. And if you compute all of those second derivatives, then you can update the weights in a more sophisticated way. So roughly speaking, the way conjugate gradients works is you calculate that matrix of second derivatives. You approximate the error landscape with some sort of like a mixing bowl, like a hyperbolic, a parabolic. A parabolic shape, and then you sort of go directly to the minimum of that parabolic shape. That's sort of roughly how it works. Now, these methods, if you've only got 20 weights or 100 weights, then these methods are okay. But in modern deep learning, we often have, it's not uncommon to have 1 million weights, right? So if you've got 1 million weights, this is just out of the question. Because the number of second derivatives is proportional to the square of the number of weights. Right? If there's 1,000 weights, you'd have to calculate 500,000 second derivatives, and if there's 1 million weights, you'd have to calculate 500 million second derivatives. So for deep architectures with lots of weights, we can't really do this. Yeah, but for some smaller problems with fewer parameters, these methods are used. Any questions? Good. Okay, so we'll take a 10-minute break, and then we'll start talking about how to look at the geometry of hidden units.
Two questions.
Yeah.
I was watching Andrew Ying's lectures and where he mentioned there's factorization and explicit loops. And why is factorization faster than
Oh, I see what you're talking about. You're not talking about a recurrent architecture. No, loop. Yeah. So NumPy, it tries to figure out which things can be done in parallel and which things can't. And it tries to do as much in parallel as possible. And I think if you've got a GPU, it tries to make decisions based on the size of the computer and that sort of thing. So,
Surely you have to do one thing after the other anyway. Even if you're using things in parallel.
why is it fascinating? It's definitely true. I mean, what you say is really true. Like, even, I saw an example recently where, Alex, a colleague of mine was doing some signal processing with Mac. Another colleague of mine who specializes in concurrent processing was able to speed his by getting rid of a loop and replacing it with a matrix model. If you can change a loop into a matrix multiplication, it's definitely going to happen much faster. But you have to have the size of the matrix. If it's too big, the size of the matrix has to be something that will fit into your architecture, your computer. It has to be big enough that you can do it like in parallel. It has to be small enough that you can do it in parallel.
Is it based on the idea of exponential weight?
That's right.
Like even if I'm watching videos, I still don't understand that.
Whether you call it exponential, I suppose it is exponential decay actually. The weight, if there's no reason for that weight to be big, it will decay exponentially.
Because I think it's usually with you start to shoot alternating, try to go straight in, but you don't want to go in. You want to all the shoots in the y-axis, but you want to go faster in the x, at the same time you want to go faster in the x.
I mean, another thing about this weight decay, sometimes the problem might be under the surface. There may be some weights that actually aren't used at all, or certain directions that are not used at all. So there may be multiple sets of weights that all produce the same minimum error, but then adding the weight decay makes it unique usually. There's usually a unique set of weights of minimal size.
I haven't got to that one. How many layers and how many nodes do we have?
There's no theoretical way to do it. You just have to try it and see what happens. It's all a bit of a
It's similar logic, yes,
right. Would be right. So normally we treat the bias is the same as the other weights. So they also decay at the same decay rates.
also they're incorporated areas.
That's right.
Okay. And actually, one question. You said that for large values,
Yeah.
for smaller weights, they can apologize from
Yeah.
But this curve kind of looks linear. So then the asymmetrical pressure is more linear.
That's right.
So I think based on the close-value relationship, if your activation functions are linear, there's no need for any units.
That's right.
So then wouldn't this be with small weights?
It's a good question. It's actually a question of balance. So if there's too much weight decay, you'll stay in the linear region, which is not good.
Okay.
You want to just find the right amount so that you sort of, what you really want to do is be kind of here. You want to have some linearity, but not too much. The weight decay, again, it's often just trial and error. If the weight updates were random, I mean,
if the weight updates were just completely random, then there'd be a theoretical way of saying what the weight occasion made. But as soon as but in a real situation, the weight updates are not random, and so the formula doesn't really do it right. Unfortunately, it's just a matter of trial and error. I mean, either next week or the week after, it's all about fractional realization and stuff. They actually explicitly try to keep the distribution with a particular standard deviation. You wouldn't have a problem with saying that's right. But having said that, sometimes I have sometimes seen people use weight decay with values, but I'm not sure. It often you often do see it done, but the benefit you often find that they would have got pretty similar results without weight decay, but maybe as the weight decay increase the performance of the but I'm not sure why. In the case of review, that's a good question. I'm not sure why, but it may make it slightly more likely for some activations to click. Yeah, it's probably not very good what the weight is. Yes, right. Exactly. That's right. Well, it may come up later, but in this situation, it's just about the weight decay. So before we even see any data, we have a prior assumption about what weight that we prefer a small weight over a big weight. We have a prior assumption about what.
It will be something go to the minimum value max cost. Pick up the random weights based on the weight. We are spreading.
That's right. Sorry. Yeah, you can have a look. I think I got the section. Yeah. Well, I don't know if all the topics are covered in here, but. Weight decay should be in there.
So we are following the chapters sequentially or just randomly?
Not quite randomly, but I've tried to make it sequential as much as possible, but it's not always possible. Weight decay. Oh yeah, they call it regularization. It's in the 5.2.2. Yeah, weight decay. There you go.
Can I just see?
Yeah, sure.
Yes, about the momentum.
Yes.
So it is to avoid the local minimum.
to the global minimum,
Right.
like you give it a push. But what if it's already in the global minimum and after the push it goes to another with a higher local minimum? Would that be possible?
It is possible, but the theory is if you're in the global minimum, then every time you do a different sample, there should be just randomly the sum of several. If you're in the global minimum and you take 10 samples, the sum of the gradients should be approximately 0, so it shouldn't take you anywhere. In fact, the momentum might actually help you to stay in the global minimum. Because if you didn't have momentum, you'd be sort of bouncing around with each training item. But if you've got the momentum, you're actually more likely to stay in it because the conflicting components from different samples are cancelling each other out.
I'm really curious about how does this momentum work? Because previously you say like it's vibrating, and how do you make the vertical force to put it to the right angle?
Well, just the sum of these vectors should. The conflicting components of the vectors should cancel out, and the ones where they agree should.
So how does this cancel? Really, can you show me on this formula? Can you just go up a bit? So it's really so
This is a vector.
okay.
Right, so if these two things are in the opposite directions, then you get a cancellation. But if they're in the same direction, then you get a reinforcement.
So these two are the different vector for the different iteration or what?
Exactly, yeah.
And
Different samples.
and that's the previous simple calculation for the previous.
Right.
Okay, so that's the momentum, and that's the previous one.
That's right. So if alpha is 0, then you just get the normal gradient descent.
Okay, so that's the for a different sample, and they may just conflict.
Right.
Or, okay. It's kind of just curious about how does it really work.
If you think about it, you should think about it as a vector, vector addition.
Different angle and
So the directions in which they differ are cancelled out, and the ones in which they're the same are amplified. Think about it. Okay, so so what I want to do now is talk a little bit about how we can analyze or visualize the geometry of hidden unit activations. And then I'm going to talk about the limitations of two-layer neural networks and a couple of ideas about how we can move up to multi-layer neural networks. Okay, so I'm going to talk about this encoder task. So this serves two purposes. So for our purposes today, the main benefit of this task is that it's just a tool for us to, it's a simple situation in which we can have a good visualization of the hidden unit dynamics. But it's also, when we get to the very end of the course, we'll be looking at other encoder networks that are also based on this principle, that are a little bit more kind of sophisticated. So the idea here is that you have a network where the input is the same as the target. So but you have a hidden layer which is like a bottleneck. So you might have a 5-dimensional input and then like a 3-dimensional hidden layer and then a 5-dimensional output. And the network is supposed to take the 5-dimensional input, compress it, squash the 5-dimensional input into a 3-dimensional space, and then expand it out again to a 5-dimensional space. So it forces the network to do some kind of compression. It forces it to kind of extract out features of the input. The hidden units will naturally end up extracting out certain features of the input once the thing's been trained successfully. So this is called an NMN encoder test. So N is the number of hidden input units and the number of output units, and M is the number of hidden units. So what's drawn here is a 5-3-5 network, but we've got to have any values for N and M. And often we just have a kind of what's called a one-hot encoding. So we just have 5, or at least for this visualization task. So we have 5 different inputs. Each input has one of these, 5 different training items. So there's no difference here between the training and the test set for this example. The 5 different training items, in each case, one input is 1 and the other, one node is equal to 1 and everything else is equal to 0. And then the output is the same as the input. Okay, so we're going to just kind of explore what happens when you train, or imagine what happens when you train one of these things. So here, these are meant to be 2 hidden units. Oh, sorry, what happened? We're on a holodeck. Here we go, okay. So these are my 2 hidden units. So hidden unit 1, let's say this is H1 and that's H2. So what's drawn here is the activations of H1 on this axis and H2 on that axis. So we could start by just imagining, we could sort of think of adding these things one at a time. But let's start with just 2 inputs and 2 outputs. So there's not really a compression going on here. And then the training items would be 1, 0 and 0, 1. And remember, the target output is always the same as the input. So we can visualize this with little, with little, points and lines. So this is the way we think about this. So the first training item is 1, 0. So when we present the first training item, this thing here is 1 and that thing is 0. So if I basically the activation of this hidden unit is going to be based on this weight and that weight. So these two weights here are not going to play any role at all. Because this input is 0, that weight and that weight are not going to be visible. So all we have is this weight plus the bias and that weight plus the bias, and then we have this activation function. So the weight plus the bias, and then we have the activation function, which brings us back into this bounded box. And so we can kind of, in a way, we can represent this information as just like a point in this two-dimensional space. You know, if I present 1 here and 0 here, what are the two activations of what's the activation of this hidden node and this hidden node here represents a point somewhere in this space. And then the same thing when I present a 1 here and a 0 here, then these two weights are going to be irrelevant, and it's only these two weights and the biases that are active, and I'll get some other point in this two-dimensional space. So I can kind of, I'm not seeing all the information, but I can see most of the information about this input to hidden layer is captured by looking at these 2 points. Okay? Now, what about the hidden to output layer? Well, the hidden to output layer is very similar to the perceptrons that we talked about in the last 2 weeks. So if you look at, say, this particular output here, it represents a linear function of these 2 hidden nodes.
Activation function.
Sorry? With the activation. Yes. It's with the activation. Right. It's with the activation function. Right. Good point. So what is actually... yeah, that's a good point. So let's think about it. We can draw. Well, what I'm saying here is we can draw this as a line. Now, okay. So if it were a perceptron, then the output would literally be 0 on one side of the line and 1 on the other. Now, because we have the sigmoid, it's not actually 0 on one side and 1 on the other, but it's kind of there would be, it would be equal to 0.5 on the line, and then it would sort of diminish towards 0 on this side and increase towards 1 on that side. But by the time we got a little bit away from here, this might be very close to 0, and that might be very close to 1. Yeah, so what you've got to think of is a kind of, you think of a sigmoid function laid flat here like this. So it's sort of like, sorry, let me get a blank piece of paper. Yeah, you think of a function that's kind of shaped like this, and then you put it like this. So it's 0 here and then goes up to 1, and this line represents the orientation of that function. Yeah. Okay, so if you think about how this is trained, you know, we want the first output. So when the first input is presented, the hidden units have these activations, and then we want the first. Then the output should be this. So the first output should be 1 for this hidden activation, and it should the second output. So if this line is the first output and that line is the second output, the first output should be 1 for this and 0 for this, and this output should be 1 for this and 0 for this. So you imagine that if this is the first output, yeah, it sort of tries to produce a value of 1 for this and 0 for this. You imagine this line here, and it's like 0 and then increasing to 1. And here, it's like 0 here, and then increasing to 1. So it produces 1 for this and 0 for this. Okay, with 2, it's a little bit impoverished, so it's a bit hard to see what's going on. So now I'm going to add a new input and a new output, but keep the same number of hidden nodes. So my training items now are 1, 0, 0, 0, 1, 0, and 0, 0, 1. So now I have three points instead of 2. So 1 point corresponds to this, 1 point corresponds to this, and 1 point corresponds to this. And then each line, effectively, the line determined by each output has to separate out one of these points from the others. Yeah. So we end up with geometric situation like this, you know, and if we try to achieve the biggest possible separation, then it might be like this. Okay, and then we can just keep going with this. So let's say we added a fourth input and output, then we get this. So you can kind of see what's going on here. So we get those 4 inputs and these 4 outputs. And then it starts to get a bit interesting. So if we have a 5th point, it is possible with a 5th point like this. I think well, the hidden units are in 2 dimensions. So what you're trying to take a 5-dimensional input and squash it into 2 dimensions and then expand it out again.
What's the point of doing this?
Sorry? What's the point of doing this? Well, the main point of this is just to get you used to the idea of seeing this kind of geometry. So we represent the input to hidden units as points, and we represent the hidden to output units as lines. And then in a couple of weeks, we're going to be talking about recurrent networks, and then you look at the way the hidden unit dynamics sort of move around as you present a series of inputs. Yeah, so it helps to kind of train your geometric intuition. The main point of this is to train your geometric intuition about hidden nodes. But as I say, these kind of auto-encoded, when we get to the end of the course after the break, we're going to look at actual serious auto-encoders where you actually have an image. Yeah, the input might be an image, and then the hidden nodes are a smaller dimension, and then you try to recreate the image. So in that case, it is actually trying to extract, it is really trying to compress the image and extract out some serious features. Yeah, so this obviously this is a toy problem, but this idea can be scaled up to something quite serious. Yeah. Yep. What role do the hidden nodes play in the diagram? Oh, changing the number of hidden nodes. Ah, good. Okay. Well, the best way. Let's push this a bit further. Okay. In a minute, we're going to go to 3 hidden nodes, but let's just see what happens. I think 6. The other thing is this kind of shows you when you reach the capacity of the network. So I think 6 would be about the limit here. I think we can fit 6 because we just kind of do it like this. You can kind of see that 6 will fit, right? But if I try to do 7, the thing would break, I think. It might break. I'm sort of straining the capacity of the network here. Okay. Now you asked. I think you're sorry. Go on.
You
You could probably fit. You could probably fit. You think you could fit unlimited? I think maybe you could fit unlimited by just having them in a circle with. But the thing starts to become more and more unstable. Yeah. Sorry. I think you're right. Theoretically, you could represent any number, but if you train the network by backpropagation, it might become unstable. It might learn the solution and then lose it and then learn it again. Yeah.
Do you get some form of aliasing?
Sorry, yeah. The question, aliasing.
If you try and compress too much input for an output, will you
Yeah.
get aliasing between the inputs and outputs?
You would get, that's right, exactly. If you try to compress it too much, you would get aliasing. You would get, well, it basically, you put in one input, but then you get out, the output, maybe what you get out is equal to an input, but it's not the input that you used. Yeah, but aliasing is a fancy name for that.
I got a slight question.
Yeah.
Is that true? So does that mean like the more circular units you have and the more nodes you have, the better the prediction will be?
Yes, the more hidden nodes you have, the greater the capacity of to store a bigger variety of inputs. Since you guys are interested, because you guys are interested, I might just mention a couple more things about this. I mean, if you really want to store a lot in here, this is actually not a very good encoding. There's a much better encoding where you have half ones and half zeros. So people have said, let's say I want to store 6 things. Maybe, I mean, this is just, again, this is really just games. This maybe doesn't have a practical purpose, but I've seen some colleagues of mine at the University of Queensland did it this way. They had 6 inputs, but they represented it like this somehow. Each input was a combination of 3 ones and 3 zeros. Right, so I've got 6 inputs here, and each one is represented by 3 ones and 3 zeros, and that actually leads to a much more stable representation because it looks like this. Did I get it right? Maybe you need, maybe to really see this properly, you need 7. Let's have 7, and then each one has 3 ones and 4 zeros. Maybe it's easier to see it that way. So I don't know if I even brought 7 sticks with me, but you end up with something like this. I don't know. I think that's it, yeah. So you can actually, if you use this encoding, you can actually encode a lot more things more stably.
But then like these 2 sticks are the same.
Is there 2 the same? Is there? Which one?
The one on the top and the ultimate one.
Did it? Maybe I got it wrong somehow. Have I got 7 sticks or 8? Which one am I missing? Sorry. Maybe that's it. Are they all different now?
But then you have only.
I'm not sure. Yeah. You get the idea though, yeah. What happened? Is this right? No, 2 of them are still the same.
No, that's the same.
Is that the same? Is what? Are there still 2 that are the same?
Yeah, it's the same as the one with the ends touching. Oh, no, that's good. Yeah, there's a coin in between that's shiny.
Oh yeah, sorry. Oh, sorry. Yeah, there is a coin here. It's we go. Sorry, I didn't realize. Okay. Yeah. All right, but who asked about the three? Okay, so just before we move on, let me ask this question. If you had 3 dimensions and 8 let's say you had 8 inputs, as each input is 1, 1, and 7 zeros, right? And you have 3 hidden nodes. What geometry would emerge from that? Let's think about this. So you've got 8. If you've got 3 hidden nodes, you would have a cube, and each coin would go to, the cube has 8 vertices, so each coin would go to 1 vertex. And then what solid would and then instead of lines, we would have planes. So I should have brought a picture of this, but I think it would form something called a cube octahedron. Let me Google this. Yeah, there we go. Sorry, let me just... well, we're going to go back to the computer anyway. Yeah, this might help you to visualize this. So every coin would go to a corner of the cube, and each plane would kind of chop off one corner, because remember the plane is trying to divide one corner from everything else. So the green lines there the green planes actually represent the 8 planes for an 8-3-8 encoder. Does that make sense? Yeah. Okay. Yes?
Is that possible to identify the feature's importance by playing with the number of hidden nodes and seeing its weights on each one?
I think so. I mean, this is, so when we, like I say, we're going to get to autoencoders. So what happens with the autoencoders, we have a bunch of images and we put them in, and then the idea is that if you choose a random point in the hidden space, then it should produce some new image, which you hope will be similar to the ones that you trained it on, but maybe not quite the same. So the more hidden nodes you have, the greater variety of images it can store. But if you have too many hidden nodes, then it may start producing images that are too different from... Yeah, if you have very few hidden nodes, it'll produce images which are like look very realistic, but are not much variety. If you have too many hidden nodes, the images a lot of variety, but they're not realistic anymore. So it's kind of, you want to have a trade-off there. Yeah. Good question. Good. Okay. So we're up to slide 3, but I think it is useful to have this kind of exploration. Okay, so now if we move to a slightly bigger neural network, so this is the network that I mentioned before that was trained for autonomous, early work on autonomous driving, and this is so this is called a Hinton diagram. So we couldn't, in this case, the number of inputs is 960. So it's not easy to visualize a point in 960 dimensional space, but Jeff Hinton sort of figured out this kind of way of doing it, right? So each point in this diagram represents a weight between, so we've picked a particular hidden node here, and this part of the diagram represents all the weights from all the inputs to that particular hidden node, and this represents all the weights from that particular hidden node to all the outputs. So we've ignored the other hidden nodes, we're just selecting one, but we're looking at its relationship with all the inputs and all the outputs. Yeah, and this tells us, this gives us a Hinton diagram, right? So the white points represent positive weights, the black points represent negative weights, and the size of that dot represents the size of the weight. So a big white dot is a very positive weight, and so on. And this kind of helps you to understand a little bit the way the network is working. But as I was saying last week, these weights often represent not a specific. Sometimes they do represent a very specific kind of input, but sometimes they represent a kind of superposition of inputs, right? So in this case, there's two different road positions that would cause this to have a high activation. So a road in this position would cause it to have a high activation, but a road in this position would also cause it to have a reasonably high activation. So you get this kind of superposition. Now, and we can draw these Hinton diagrams for various other networks. So again, these are very simplistic networks from the 1990s, but it's useful to go back and have a look at them and how what the hidden units looked like. So this is very early work, I think, that was done in Cornell University or possibly CMU, where they take a two-layer network and they just train it to do. They train it on two tasks. So they just took a few pictures of people in their department, and they asked each person to make 4 different poses. So they asked them to look straight ahead, left, right, and up. And they trained one network to try to identify the person, and then they trained another network to try to guess whether the person is looking left, right, or up. Okay, so the input, and these are very low resolution images. I think they're 32 by 32, and you have only 3 hidden nodes and then 4 outputs. So it's quite a simplistic network. But it's interesting. This is the kind of diagram that you get out, and if I can expand this a little bit, yeah, you can sort of see. So let's look at the top bit first. So this is a Hinton diagram for each of the hidden nodes. So I'm trying to figure out what this actually is doing here. So left. So this this node here is very likely to represent a person looking up. So somehow this is some kind of superposition of nodes where the person's looking up. This node is, I don't know. It's a bit hard to see what's going on here, but this is sort of a mixture. This is kind of a mixture of people looking. Oh no! Wait a sec. If you look at these specific examples, so if a person's looking to the right, then this part of the image is more likely to be white because that's going to be their face. And this part is more likely to be black, So I think this node is kind of going to have a high value when the person is looking right, but probably a low value when they're looking left. Yeah, I think this node is going to have a high value when they're looking up, and that's going to have a high value when they're looking down. Yeah. So it's pretty weird. This is sort of related somehow to eigen. I mean, this is slightly non-linear, but there are other methods where people do singular value decomposition, and in which case these would be eigenvalues of a particular matrix, and so they're sometimes referred to as eigenfaces. Yeah, so you kind of get the idea. And it also shows you which part of the image is important. Like the gray areas are the part of the image that the network virtually ignores. Yeah. Okay, so what else can we say about the network geometry, or the geometry of these activations? Well, there are a lot of symmetries in these networks. So let's suppose if you have a network with let's say you have a network with 10 hidden nodes. Well, if I were to swap 2 of the hidden nodes, you wouldn't notice you wouldn't notice the difference, right? Because the input, if I were to take all the weights coming in and out of this node and swap them with all the weights coming out in and out of this node, then the overall function of the network would be exactly the same. Yeah. So that's sort of interesting. So if there's 10 hidden nodes in your network, that means if I give you one set of weights, if you give me one set of weights that achieves the minimum and the cost function, I can automatically give you 3 million other sets of weights which achieve exactly the same cost function. Because 2 to the 10, I can permute those 10 nodes in any combination, and the number of combinations of 10 nodes is 10 factorial, which is about 3 million, right? And then, so the minimum is certainly not unique, right? Now, I can also reverse the sign of all the incoming weight. If I pick a particular node, it's easier to see this when we have a symmetric transfer function like tan h. If I pick a particular node and I reverse, let's say I pick this node and I change all these weights to be the negative of what they previously were, and I change all the outgoing weights from that node to be the negative of what they previously were. Well, again, you're not going to notice the difference because whenever I present an image, this node will have the negative of the activation that we would have previously had. But then these weights are also negative, so its effect on the output node will be the same as what it would have been. Now, if we have the sigmoid function instead of tan h, it's not just a question of taking them. You have to account for the bias as well. You have to make some adjustment to the bias, but there is a way to change the weights in such a way that the effect is the same. So that means, so where were we? So with those 10 hidden weights, I can permute the weights any way I want, and I can also reverse the sign of any particular weight. I can permute the hidden nodes any way I want, and I can reverse the sign of any particular hidden node. So that gives me there's 2 to the power 10 ways of permuting nodes. So I've got 1,000 ways of changing the sign of different hidden nodes, and I've got 3 million ways of permuting them. So there's actually 3 billion sets of weights which would do equally well. Yeah. So this just helps you to understand the geometry of high-dimensional space, I guess. Well, here's the other thing about these hidden nodes. So if you think about training by let's suppose, think about this hidden node and this hidden node. let's suppose that at the beginning of the process, the weights coming into this node are exactly the same as the weights coming into this node, and the weights coming out of this node are exactly the same as the weights coming out of this node. Now, when we do our back propagation, because the weights of this node are the same as the weights of this node, the gradient of these weights is going to be exactly the same as the gradient of these weights, and the update of these weights is going to be exactly the same as the update of these weights. So if I train with all my input data, it'll still be the case that these two hidden nodes are identical. So we always have to break that symmetry. So this is why when we start the training, we can't start with all the weights equal to 0 because they would remain 0. What we have to do is we have to start the weights with random initial values so that each hidden node is a little bit different from the other hidden nodes. Yeah.
That apply to both batch and online learning, or just batch?
It does apply to both batch and online learning, because the batch, with the batch learning, it's parallelized, but it's still the case that the weight updates are going to be exactly the same operations are happening to the weights of each of those hidden nodes. So they would still remain.
What about with online learning?
With online learning, I think it would still happen because you present one item, but it affects both the hidden weights the same way. Yeah. So it doesn't really matter if it's batch or online. Yes?
So what if during the learning process they end up becoming the same? Will they continue being the same?
Yes. So the question was, if during the learning process they became the same, would they stay the same? The answer is that they would, but the chance of them, in practice, there's a kind of butterfly effect. If they start out just slightly different from each other, then they will diverge. Yeah, so the chance of them, it's very unlikely that they would actually come together. Yeah, once they're apart, they probably will stay apart. Yeah.
So what kind of distribution we need to choose for the initiators?
What kind of distribution? Okay, so the initial weights, so usually we choose a Gaussian distribution for the initial weights with a fairly small standard deviation. Sometimes people use a uniform distribution, but I think a Gaussian distribution is better.
Yes, if we choose a Gaussian distribution, it will still make some weights the same.
Some weight, it's only a problem if okay, let's say there's 900 weights coming into this unit and 900 weights coming into this unit. It's only a problem if these 900 weights, if all 900 of these weights are the same as all 900 of the other weights. Yeah, if there are just one weight here that's the same as one weight there, then it's not a problem. Yeah. Yeah.
So if you're looking at the diagram, how are you supposed to read it? The different dimensions, exactly.
The Hinton diagram.
Yeah, you see that. You've got x, you've got things in multiple dimensions. You've got an x and y dimension.
Yeah.
How are you supposed to read it? And look at what's supposed to be in the output. Is each of those a set of hidden nodes, or?
So the Hinton diagram, the input is actually an image, and so the network is not really aware of the spatial relationship between the pixels in the image, but we are when we look at it. So
that's representation of the image.
That's right. Exactly. Yeah. Where was I? I don't have a video of this, but the Right, so someone was asking about whether the things could come together. So if you actually, like if we look at that encoder task and you actually train the network, what would, maybe I'll, you know, I should actually try to generate a proper video of this, but this, let me just demonstrate to you what would happen. So all of these points start out very close to the middle, and then after you train, what actually happens is they'll sort of split into clusters. So it might split like this, and then a bit later it might split like this, and eventually they all kind of separate out. So you get this funny kind of thing where they sort of split off and into little groups, and then the groups split up. And that's sort of kind of typical of what happens in training in general. Yeah. So these hidden nodes start out doing very similar jobs, and then over time they differentiate. Okay, I think that's what I said here, yeah. Yeah, so this just gives us a little bit of a help to kind of visualize these spaces. What else can we say? So when the weights are small, so remember this activation function, at least these sort of sigmoid or tan H function that we've talked about so far, for the small values of the weights, the function is approximately linear. And so the whole network is kind of implementing an approximately linear function. Now, as the weights get a little bit bigger, you start to get more and more non-linearities. So the idea is to achieve this kind of trade-off where someone was asking, like I was saying, if the weights are too big, you get out into this region where everything is like extremal. And then someone at the break was saying, well, but yeah, if the weights are too small, then you're stuck in the linear region. So the aim really is to try to achieve a balance where you have the weights where the activations get a little bit into the nonlinear region, but not too far. And in a couple of weeks, we'll talk about certain processes like batch normalization, where you actually try to explicitly achieve a certain standard deviation for each hidden unit activation over the training set. Okay, so that's the geometry. Now, the other thing I wanted to talk about is the limitations of two-layer networks and the potential for multi-layer networks. So in the early days, people almost always used very few layers in their neural network, usually 2 layers, sometimes 3. Now, why is that? Well, first of all, okay, so actually, to be more specific, people most commonly use 2 layers in their neural network. It was even a bit unusual to use 3. Now, what are the limitations of a 2-layer neural network? Well, this is a specific data set that was invented around 1989 just for the purpose of trying to visualize something that can't be learned by a 2-layer neural network. So the idea here is you've got 2 inputs, which are the x and y coordinate of these dots, and the network is supposed to output either 0 or 1. It's supposed to output 1 for the blue dots and 0 for the red dots. Right, so this is called the twin spirals problem. And it turns out if you train a 2-layer neural network on this, it actually fails. It can't learn the task because it's too complicated. But it is possible to learn this if you have a 3-layer network and if you have shortcut connections between the layers. So this is the simplest network architecture that's capable of learning this. So you have 2 inputs, you have the first hidden layer, the second hidden layer, and then the output, and every node is connected to all, not just the nodes in the previous layer, but the nodes in every layer. So, right, so sometimes we build up a network in such a way that like the nodes in the first layer are connected only to the inputs, and then the nodes in the second layer are connected only to the first layer and not to the inputs, and the third layer is only connected to the second layer. So often we just work layer by layer, but in this case we've actually included these shortcut connections. And again, this is an old idea which in recent years has actually come back in the form of dense networks. So people are actually using this kind of thing for image processing. But if you have each node connected to all previous nodes, it is possible to learn this. And again, we can, yes?
For the previous one,
yeah.
When we say that this is the smallest one that can solve, have we said that from experience, or can we theoretically somehow?
Good question. So the answer is it's basically from experience, but we can kind of do some analysis. I mean, when I talk about terms like convex and concave here, it's not that easy to make these things precise, but it kind of this kind of gives you an idea of what's going on. So what happens when you train this? The first layer, if you train this and then try to analyze what's going on, the first layer learns linearly separable features of the inputs, right? And then the second layer, it kind of learns convex features. So typically these second layer neurons will so the first layer neurons, you've got a line and you've got the positive values on one side and the negative on the other. The second layer features, you've kind of got a region and the inside is positive and the outside is negative, or vice versa, but usually it's a convex region. But then the third layer, it may include, so convex, it doesn't have like holes in it sort of thing. But the third layer can include holes, so it can have like concave regions. Yeah, so these are not really sort of precisely defined terms, but this is roughly the kind of features that emerge. Yeah. Okay, so there were some examples like this where you could take a 3-layer network and train it and get a successful result. But even to train something as simple as this, like you had to be very careful with your training. The network weights had to be small and the learning rate had to be slow. And it was easy to mess it up. If the learning rate was too high, the thing would fail to learn. It would get stuck in a local minimum. So it's very kind of finicky. And it was generally found that so this was found to be a general thing in most neural network architectures. The things that we talked about where we had the Pima Indian database and all these kind of traditional problems, you train a 2-layer network and maybe it's not adequate to do the task, and then your initial thought is, well, I'll just add more layers. I'll make a 3-layer network or a 4-layer network or a 5-layer network. But in reality, those efforts often failed. And this was sort of a sticking point. The research kind of got stuck here for a few years, and then eventually kind of modern techniques were developed. But it's important to try to understand, the nature of these problems. So why did it fail? Well, it failed because of this problem that we refer to as vanishing or exploding gradients. So if you have a network with a lot of layers and you're trying to train it by backpropagation, typically what would happen is that, well, two things could happen. So the problem of vanishing gradients. So you start out here, you have a gradient here, and then you back propagate to get a gradient here, and then a gradient here, and then a gradient here. It would often happen that the gradient would get smaller every time you went back through a layer. And so if you had a lot of layers, the gradients are getting smaller and smaller, so the lowest layer isn't really learning very effectively because the updates are too small. Now, on the other hand, if you sort of crank up the learning rate or increase the number of hidden nodes, then you may get the opposite problem. The gradients may increase at each level. So you might have a gradient here, and then the gradient might be twice as big at the next layer, and then twice as big, and then twice as big. So then this becomes the problem of the exploding gradients. So then the weights at the lowest level kind of blow up to large values, and then that kind of stuffs up the learning. So this was a problem that people really struggled with around sort of the late 90s and early 2000s. And so there were a number of different things that helped to alleviate this problem. So today I'll just talk about a couple of them, and then we'll get to more of them later on. So one solution came in the form of what's called layer-wise unsupervised pre-training. Well, since we talked about autoencoders, maybe it's worth mentioning this. So the idea with this layer-wise, one way of doing this layer-wise unsupervised pre-training is like this. So I have some images, let's say, or some set of inputs, and I train one of these autoencoders. And then after I've trained it, I take off the top layer and I use just this part of the network as my as the first layer of a larger network. And in fact, I can do this iteratively. Once I've got these weights, I could build a larger encoder network, and so I haven't looked at the outputs yet at all. All I've done is look at the inputs, but this gives me a set of weights for this from the inputs to the first hidden layer, and then I could add a couple more layers on top, and then I train the whole thing by back propagation, and this actually kind of gives a better result because I've already done this unsupervised pre-training. It gives these hidden nodes already kind of extract out certain useful features. Okay, we'll talk a lot more about this later in the course, but that's the idea. There's another thing called long short-term memory. This is specific for recurrent networks. So we'll get to recurrent networks in week 5 of the course. And another thing was new activation functions. Okay, so let's talk about the new activation functions. Now, these are the ones we talked about so far. We had the sigmoid and we had the hyperbolic tangent. Now, interestingly, an activation function that started to become popular around 2012, especially for image processing tasks, is this activation function here, which is called a rectified linear unit. So this, for x bigger than 0, this is equal to x, and for x less than 0, this is equal to 0. Now, this kind of, when you first see this, it kind of looks a bit crazy, because the thing is, you could see the thing's not differentiable at that point, and there's a risk here that if too many hidden units end up in this region, then they could become kind of dead. So this looks quite radical, but somehow, if you have a deep, it turned out that if you have a deep network with 8 layers instead of 2 or 3, you often get a better result using this than one of these. Yeah. The reasons for there's been some analysis done on this, but the reasons aren't fully understood. But I guess it's sort of it's easier computationally to compute this, but the reason it sort of solves the vanishing and exploding gradients problem because the thing is kind of linear on one side. So some parts of the network are computing a linear function, and other parts are computing or just 0 and not contributing at all. So somehow this prevents the weights from blowing up. And yeah, this thing here is another, this is a more recent one that was just introduced last year and has become popular, excuse me, for some tasks called the scaled exponential linear unit. So it's linear on this side, but instead of being 0 on the other side, it has a kind of decaying exponential. And the parameters of this linear function and the decaying exponential are specially chosen to preserve the standard deviation from one layer to another. It's quite, there's a quite complex paper describing this. Okay, so that's so in the traditional models years ago, people used 2-layer networks with sigmoid or hyperbolic tangent. ReLUs have become much more popular these days, and people are still kind of debating about these scaled exponential linear units. Some people say they're really good, some people aren't convinced. There's still sort of work going on there. All right, so I think what have we got? I've probably got time for one more topic. I think what I'm going to do, I think I'll leave dropout to next week, but there's one topic that I did want to cover because it's kind of useful for the assignment, which is softmax. So I'm just going to jump ahead to this slide from next week. It's a little bit out of order. Okay, so what's the context of this? So if you look at the data that's being used for the assignment, it's this data set that's become quite common. It's from the Canadian Postal Service, and it consists of handwritten digits. So these are some examples from that data set. There's actually, I think, 50 or there's either 5,000 or 6,000 examples of each digit that's taken from people's writing on letters. And so the total data set is either 50 or 60,000. Sometimes people train on 50,000 and test on the other 10,000. And so the task here is that the input is one of these digits, and there are 10 outputs, and it's a classification task, but with 10 different classes. And so we've got 10 different outputs. One output says that the thing is 0, and the next one says it's a 1, and then a 2, and so on. So you've got 10 outputs. Now, we discussed about cross-entropy for classification with 2 classes. So here we've got 10 classes. There is a generalization of cross entropy that applies to multiple classes, but it's become more common to use this method that's called softmax. Okay, so the way this works is that you get 10 outputs Z. Let's call them Z0, Z1, Z2 up to Z9 because it corresponds to those digits. And remember that they can be positive or negative. So we want to interpret these as probabilities, but it doesn't sort of make sense to interpret the output itself as a probability because it could be negative. So what we do instead is we take the exponential of the output. So e to the power of Z1 is interpreted as a probability, right? And that has to be positive. But the probability is proportional to e to the Z1. So there's some normalizing constant. So, and what you'll be doing in the assignment, you'll be looking at different architectures, so a linear network, a 2-layer network, and then a convolutional network. But in each case, there'll be 10 outputs. And the way we interpret this is the probability of digit I is equal to e to the power of Zi divided by the sum from j equals 1 to n of e to the zj. So to be a probability, they have to all add up to 1. So this guarantees that they add up to 1. Okay, so there's always this relationship between different outputs. If one output is if this output is 1 higher than another output, that means that it's more likely by a factor of e. Okay. And so this is what we use. So the probability, so we interpret this as a probability and then we play the same game. What we want to do is maximize the log of the probability of the correct output. And if you take the log of this expression, well, the log of the top just becomes Zi, and then we have to subtract off the log of the denominator. So we get this slightly complicated expression here where we take a sum of exponentials and then we take the log of it. Now, there's actually a nice explanation of this in the textbook in section 6.2.2. So, so the way it works in practice is this. So notice the Zi here. So if I is the correct class, then I want to increase whatever the output is that corresponds to the correct class. I want to increase it, basically, right? Because the derivative, when I take the derivative of that first term, that's going to increase all the weights that are leading into the correct class, right? So I want to increase the output for the correct class. Now, what happens with this other term is, if there's some class whose output is bigger than the correct class, then it's going to get reduced heavily, right? So if the correct class is very high and everything else is very low, those weights for the other classes are not going to change very much, actually. But if there's some class which is similar in value to, if there's some incorrect class whose output is similar in value to the correct class or even bigger than the correct class, then this term will have the effect of reducing that incorrect class a lot, right? So normally, in rough terms, what this does is it pushes the correct class up and it pushes down any incorrect class which is higher than the correct one. Okay, but in TensorFlow, you just type in that you want softmax and it computes softmax for you. But I think it's useful to know what's actually happening behind the scenes. All right, we've covered a lot today. I think we might just have a bit of an early mark here. Okay, so I'll see you next week.
I got some questions here. You see that really can prevent the vanishing?
Yeah.
Because why? Because they don't decrease the weight for some